Okay, so let's rehash where we were at previously. So, two videos back, we were talking about this reaction that you have this equilibrium between SbCl5 and SbCl3. SbCl5 is your reactant, SbCl3 is your product along with Cl2. Okay, we had talked about how do we compare the reaction quotient to the Kc to figure out how close are we to equilibrium. And then what we were doing was just trying different concentrations out. So we said, what if at equilibrium the concentration of Cl2 is 0.01 molar? How close are we to equilibrium? Well, we weren't close. And then we tried 0.02 molar for concentration of Cl2, and we still weren't that close. So what we're going to do now that we remember how to use the quadratic formula, let's apply the quadratic formula here. Let's see how this works. In order to solve an equilibrium problem, we're going to have to make something called an ice table. It's similar to what we were doing previously up here, where you have the reaction and then you have the initial concentration and the change. So that's essentially what we're going to be doing. So let's try this out. So we're going to set up an ice table for the reaction that we've been working on. So the reaction that we've been looking at was SbCl5 is in equilibrium with SbCl3 plus Cl2. Okay, and these are all gaseous. So let me write the gaseous symbols in. So initially, the concentration of SbCl5 was 0.150 molar, and initially you have no concentration of SbCl3 and no concentration for Cl2. The second line, the delta, which is change. Okay, so we know what we were doing previously was, let's say the concentration goes up by this. How do we deal with this? What we want to do now is try to figure out what is that number that's got to go down or go up. So everything on the left-hand side, we're going to say minus x. Okay. For SbCl3 and Cl2, we know that those have to go up. So the concentration is going to be x. Okay. And so E, which is equilibrium, we have expressions. So for SbCl5, we know it's going to be 0.150 minus x, and that's going to be the concentration at equilibrium. We know that the concentration of SbCl3 at equilibrium has got to be x, and we know the concentration of Cl2 also has to go up by x. Okay. And so what our job now is to solve for x. Okay. So the way we do that is to write our equilibrium expression, Kc. If we're going to write this normally, the concentration of Kc would be SbCl3, the concentration of SbCl3, times the concentration of Cl2, divided by the concentration of SbCl5. So what I'm going to do now for that expression, we're going to pop in our values. So we know at equilibrium, the concentration of SbCl3 is going to be x. Okay. We know this concentration of Cl2 also is x, divided by the concentration of SbCl5, which is going to be 0.150 molar minus x. Okay, and this is going to be equal to the equilibrium constant, which we know is 0.025 for this reaction. All right, so we can do a little bit of rearranging here. So x times x, which is our numerator, we know that x times x will give us x squared, divided by 0.150 minus x. This is going to be equal to 0.025. So what we need to do is to solve for x. To help us out, we need to use the quadratic formula. So we need to get this equation into the form of ax squared plus bx plus c is equal to 0, because once we know what a, b, and c are, we can pop them into the quadratic formula and we're good to go. So what I need to do is to get x squared by itself. So I need to multiply both sides by the denominator 0.150 minus x. So let me do that. So x squared is going to be equal to 0.025 times the quantity 0.150 minus x. All right, so now what I have to do is distribute this 0.0250 to the 1.01.150, do the same thing to the negative x. So if I multiply those two together, x squared is going to be equal to 0.0250 times 0.150. That should give us 0.00375. And then we're going to multiply 0.0250 minus x. That would give us 0.025x. All right, so we're pretty much there. We just have to rearrange this equation now so that way everything is on one side. And we get this equation to the form ax squared plus bx plus c is equal to 0. All right, so already x squared is on the left-hand side, so I'm going to subtract 0.02. I'm going to add 0.025x to both sides. So that way I get x squared plus 0.025x is equal to 0.00375. I need to subtract both sides by 0.00375, so that way everything is on the left-hand side. So that gives me this. X squared plus 0.025x minus 0.00375 is equal to 0. So that means my A value is going to be 1. My B value is going to be 0.025. And then my C value is going to be negative 0.00375. All right, so what I need to do is use a quadratic formula, which again, this is it. X is equal to negative B plus or, let me get that out. Plus or minus square root of B squared minus 4AC divided by 2A. All right, so I need to pop all these values in. So we're going to have x is equal to negative b squared, or negative b, which is 0.025, plus or minus the square root of b squared, so 0.025 squared, minus 4 times 1 times c, which is negative I'm running out of room over here, but let me write this over here. Just slightly below this, negative 0.00375. Okay, divided by 2 times 1. All right, so if I do some math here, let me again get my calculator out. What I want to do is figure out what is that number inside the radical. So what's inside that square root? So if we take 0.025 and square it, okay, which is 6.25 times 10 to the minus 4th. If I multiply this by 4 times 1 times negative 0.00375, okay, I get negative 0.015. Let me write what we got. So we got negative 0.025 plus or minus the square root of 6.25 times 10 to the minus 4th. Okay. And then minus a negative 0.015 divided by 2. Okay, so now we got to get that numerator under control. So we got that radical under control. So negative 0.025 plus or minus. Let's figure out what that radical is. So we have 6.25 times 10 to the minus 4th minus a negative, minus negative 0.15. So that's going to give us a 0.01 negative. That's going to give us a positive 0.0156. So if I take the square root of everything inside that radical, I should get the square root is going to be 0.125 divided by 2. All right, so one potential answer, and I'm running out of space, so I'm just going to make let's keep going. So one potential answer is going to be this. X is equal to negative 0.025 plus 0.125 divided by 2. And another potential answer is going to be x is equal to negative 0.025 minus 0.125 divided by 2. All right, so let's see what we get. So negative 0.025 plus 0.125, okay, divided by 2 should give us 0.05. Okay, so that's one potential answer. Another potential answer is negative 0.025 minus 0.125 divided by 2. Divided by 2 gives us negative 0.075. So those are the two roots to this problem. Now, we got to throw one of these away because remember, the equilibrium expression says this. X should be positive. So the concentration of SbCl3 is going to be plus X. Concentration of Cl2 is going to be plus X. You can't have a negative concentration. It's not possible to have a negative concentration. So right off the bat, our second answer doesn't make sense physically because you can't have a negative concentration. So therefore, only one potential answer could work. And so the concentration's got to be 0.05. So that means, following our expression above, the concentration is going to be X for Cl2, and the concentration is going to be X for SbCl3. So the concentration for both of these should be 0.05 molar. Okay, and the concentration of SbCl5, that was going to be 0.150 minus X, or that new concentration should be 0.10 molar. And so those would be the concentrations at equilibrium. Now, there is a way for us to check to make sure that this works. So remember, we wrote an equilibrium expression up above. If we know our concentrations, which we do now, if we pop them into this expression, we should be able to solve for Kc and hope that we get that equilibrium constant value. So let's do that. So Kc is going to be X squared, or 0.05 squared divided by 0.10 molar. All right, so if I get 0.05 square it, that gives us 0.0025 divided by 0.1. That gets us a Kc of 0.025, which that's the same value. So we know that these concentrations are the correct value. So that's our way of double checking to make sure that we calculate this correctly. And so that's how you do one of these equilibrium problems. It does take time. It does take time to do these equilibrium problems, but if you go step by step and go slow and get the expression, get that quadratic formula, so that way you can you get the quadratic equation, so that way you can pop in the quadratic formula and solve for X. That's going to save you a whole lot of time. Let's try another problem, okay? So this one's going to be slightly different from the last problem that we did, but don't worry, we'll still approach it the same way. So here's your equation this time around. N2, which is gaseous, plus O2, which is gaseous, yields 2NO, also gaseous. So many of us cause this reaction to go this morning because this is the primary reaction that takes place in a car engine. Okay. Now, at an elevated temperature, the reaction's Kc is going to be 0.0023. What is the equilibrium concentration for all three species if your initial concentrations are N2 and O2 are equal to each other at 0.500 molar, and the concentration of NO is at 0. So we're going to set this up the same way. Let's set up the ice table. So I'm going to write the reaction at the top. N2 plus O2 is in equilibrium with 2 NO. All right. So initially, the concentration is going to be 0.500 molar for N2, 0.500 molar for O2, and the concentration of NO is at 0. Now, for the change, we know that the concentration of N2 has to go down by X, concentration of O2 has got to go down by X, but NO, we know, is going to go up, and it should go up by X. Now, here's the thing, because everything has if we look at the stoichiometric coefficients, you've got a coefficient of 1 for N2, 1 for O2, but 2 for NO. So that means that NO should go up by 2x. Okay, so that way at equilibrium, and the concentration of N2 is going to be 0.500 minus x. You're going to have 0.500 minus x for O2, and then plus 2x for NO. So that means if I was to write an equilibrium expression, Kc would be equal to 2x for the concentration of NO, which is going to be squared, times concentration of, or divided by concentration of 0.500 minus x for the concentration of N2, times the quantity 0.500 minus x for the concentration of O2. And this is going to be equal to 0.0023. Okay, now I can simplify this a little bit, because on the denominator side, we have 0.500 minus x twice. We're multiplying each other. That's the same as saying this. 2x squared divided by 0.500 minus x squared. And that's equal to 0.0023. Okay. Now, with this equation, well, first off, we can get this into a form ax squared plus bx plus c is equal to 0 and solve for the quadratic formula. But for this equation, we do have a little bit of a cool trick here. So if we take the square root of the left-hand side, okay, that gets rid of our squares. So let's do that. But if we take the square root of the left-hand side, we also have to take the square root of the right-hand side as well. So by doing that, we get this expression, that 2x divided by 0.500 minus x, this is equal to the square root of 0.0023, which is going to be 0.04795. So now we just have to get x by itself. So let's get rid of that denominator. So we're going to multiply both sides by 0.500 minus x. So 2x is going to be equal to 0.04795 times the quantity 0.500 minus x. And if we distribute that the 0.04795, we would get 0.04795 times 0.5 will give us 0.0239 minus 0.04795x. Okay, so now if I try to group all the x's together, we have 2x on the left-hand side. If I add both sides with 0.04795, that would give me 2.04795x is equal to 0.0239. And so if I divide both sides by 0.025, if I divide both sides by 2.04795, 0.0239 divided by 2.04795, x would be equal to 0.0117 molar. All right, so that's my concentrations. Those are my x's. So if I was to put them into the equation, that means the concentration of N2 would be 0.500 minus x, or 0.4883 molar. The concentration of O2 would also be the same, so that would be 0.883 molar. And the concentration of NO would be 2x, or 0.0234 molar. And so if we wanted to verify that everything works right, we would put these values that we just calculated, we put these into the KC expression and see, hopefully, that we get the value for KC, which was 0.00, what was it, 0.0023. Okay, and then, yeah, these would work.